All right, everybody. So welcome to the sort of last summary lecture here about chapter 16. So this was maybe fashioned after 16.10 of the textbook, but we're going to say probably a little bit more than what's actually mentioned in there. So anyway, this is trying to unify these four big theorems that we've learned now. So before we do any unifying, let's first just go back and restate these four big theorems and maybe even start to look for some similarities between them all. So the first one we learned was the fundamental theorem of line integrals. And this one was about conservative vector fields, right? The vector fields that were the gradient of some scalar valued function little f. Okay? And if we had some curve, this is about line integrals, so it's integrals along curves. So if we had a curve C that had been given by some parametrization R of t, where t varies between a and b, then the fundamental theorem of line integrals said that the line integral along C of the gradient of the function little f was given by just taking the function little f and evaluating it at the endpoints of the curve and taking the difference. Very similar to the fundamental theorem of calculus, right? And I believe that theorem even appeared in the proof of this one. But notice here that this gradient, remember this, we can think of this as kind of like this vector of operators, vector of partial derivative operators. And so in a sense, it kind of acts as some kind of notion of like a multivariable derivative for us here. And so in this sense, the fundamental theorem of line integrals says, the integral of the sort of derivative of f is just take f and evaluate it at the endpoints that you're integrating along, and then take the difference of those function values. It's very similar to the fundamental theorem of calculus. And so here's kind of just a little picture to illustrate what a curve maybe in the plane might look like. So you would just take the function value at r of b and the function value f of little r of a and just take their difference. And so whatever is the curve that's going between r of a and r of b is actually irrelevant, because the line integral depends only on the function values at the endpoints. Okay, and so another nice thing you can think about here is that here we have a sort of one-dimensional integral, right? It's an integral along just a curve. When you actually compute it, it's really just an ordinary single variable integral, like from calculus 1. And what this theorem says is that we get to trade that for the difference of just two function values. And so I know this is kind of like a little mind stretcher here, but we might actually think of this difference of two values as maybe just like some kind of zero-dimensional integral of sorts. It's just a difference, or just a signed sum of a discrete number of values, or a discrete set of values, rather. It's really a finite set of values in total. That's fine, whatever. Okay, so the next one that we learned was Green's theorem. And this was about vector fields specifically on the xy plane. So the fundamental theorem of line integrals applied in any dimension of space. Green's theorem was really just specific to vector fields on the plane. So suppose that we had a closed and bounded region of the xy plane whose boundary was a simple closed curve, and we parameterize that boundary by some function, r of t, again, as t goes from a to b. And I think here, to be a closed curve, r of a would equal to r of b. Okay, and then we had to make some assumption that that parameterization gave us what they called the positive orientation. Okay, and with that in place then, we got that the line integral of f along C was equal to the ordinary double integral along the bounded region D of this difference of the partial derivative of q with respect to x minus the partial derivative of p with respect to y. Now, the reason that I wrote it this other way is that I'm trying to kind of keep it in line with the other guys here. And so, so we can think of trading this two-dimensional integral here for a one-dimension smaller integral, a one-dimensional line integral on the other side of the equation. And notice that here, what is the integrand on the left side of this equation? Well, it's some mixture of partial derivatives from the component functions of the vector field. So it might not be like some notion that we have of a derivative of a vector field on the nose right now, but it's at least something to do with derivatives. And when we take the integral of that something to do with derivatives, we can actually replace it for something one dimension smaller that just involves the original thing in question, f. Okay? And so here's kind of an illustration of what a positively oriented curve looks like bounding a region of the plane. Okay, and then I think something that we saw in maybe a lecture maybe last week was that Green's theorem was really just a special case of what we call the Stokes theorem. And so this theorem concerns vector fields in three-dimensional space. And in particular, it's looking at their curl. So how do you get the curl of a vector field? Well, you take its component functions, and then you take this gradient vector operator thing, and you take the cross product of this gradient vector operator with f, okay? And so let's suppose that we have a surface in space that has a boundary, and that boundary is just a single curve C. And let's say that, S and C are oriented to be consistent with one another, and I know we've discussed that in a previous video, so we won't harp on it too long here. But then in this case then, we say that you can trade the surface integral of the curl of f along S with the line integral along C of just f. So here's kind of a picture of a surface with just one boundary curve. So here we have this kind of hemisphere, and its boundary curve is this circle along here, so it's kind of open. There's no cap on the bottom. So notice that this is, again, where we have a derivative of sorts of a vector field, right? We have this gradient this vector of partial derivative operators acting some way on our vector field f. It's some kind of notion of perhaps a type of derivative of a vector field. And when we do an integral of that, we get to trade it for an integral of one dimension less of really just the original vector field f. So we can think of this as trading the two-dimensional surface integral for the one-dimensional line integral. And remember, too, that if we had our simple closed curve C and our surface S both lying flat in the xy plane, then Green's theorem was the exact result that we got from applying Stokes' theorem. So that integrand from Green's theorem is, in fact, the z component of the curl of f. Okay. And then the last theorem that we learned was the divergence theorem. And this one was also about vector fields on three-dimensional space, but now it was about their divergence instead of their curl, right? And this divergence is a scalar valued function where you take your vector field f and you take that that vector of partial derivative operators, that gradient vector, and you take the dot product of the two objects. Then this theorem said that if E was a solid region of three-dimensional space whose boundary was a surface S, then the ordinary triple integral over E of the divergence of f is equal to the surface integral along S of just the vector field f. So again, here we have this derivative type operator being applied to our vector field f on the left side of the equation, and doing a triple integral of that gadget gives us something that instead we could trade for just an integral of sort of one dimension less of just the original vector field f. So we think of this one as trading the three-dimensional triple integral for the two-dimensional surface integral. Now I know that in all the instances that we actually applied the divergence theorem, it was the other direction that was useful for us. We liked trading out surface integrals for triple integrals because surface integrals were generally pretty tricky to do, and all the instances that we saw in the previous slideshow had that this divergence of f was something that was pretty easy to do a triple integral of. Okay, but nevertheless, I'm going to state this theorem this way again because I still like the idea that on the left side we have the derivative of some kind of derivative of the vector field f, and on the left side we have one less dimension of integration and just the original vector field f instead. So stick around for the next talk. So now that we've seen all of the theorems again, all kind of lined up together, maybe we start to get a sense of how they all kind of are saying the same thing. They are all saying something about us having a derivative of sorts on one side and no derivative, the thing whose derivative got taken alone on the other side with one dimension less of integration. So in the next talk, we'll start talking about some formal machinery that will allow us to make sense of how all of these theorems are really kind of just small pieces of the same, more general theorem. So stick around for that talk.